We will review the basics of linear algebra. We will talk about the basic definitions and especially about linear operators and linear operator equations, and these will define most of the problems that we discuss in this course. So first, we need to talk about a vector space. A vector space is a set which has two operations defined on its elements, addition and scalar multiplication. These operations, addition and scalar multiplication, are closed. What this means is that if you add two vectors in a vector space, that summation is also going to be an element of the space. And if you multiply a vector by a scalar, then that result is also going to be a vector in the vector space. In this class, scalars are going to be real numbers unless we specify otherwise. Vectors are usually denoted by bold-faced lowercase letters. Elements of a vector space also satisfy 8 various properties, all of which can be found in your textbook on page 36. These properties are exactly the things that you would expect. These are things like commutativity, associativity of addition, the distributive property, the fact that a zero vector exists. All things that you would probably come up with yourself if you were to define a vector space out of thin air. So some examples of a vector space. The most common one, and one that you saw many times in linear algebra, is the Euclidean space. This is the set of all n tuples where the coordinates are real numbers. Now, you know Euclidean space, you know Rn very well. However, what's going to be much more useful for this class are in fact the function spaces, and these are vector spaces that are made up of functions. So some examples that we're going to be talking about a lot in this class include the space of all continuous functions defined on an interval AB. This is represented by the notation CAB. Another example is all differentiably continuous functions. So functions whose derivative is continuous over an interval AB. And then finally we have k-differentiable functions, where the first k derivatives are continuous. In particular, as you can kind of tell from the heat equation and the boundary value problems that we've discussed thus far, we are going to be considering C2 mostly, functions that have two continuous differentiable or derivatives. So next we're going to talk about subspaces. A subspace of a vector space is simply a subset of V. That has a couple of extra properties. First, the zero vector belongs to that subset W. Second, if we have two vectors inside of W, x and y, and we have two scalars, alpha and beta, then alpha x plus beta y will also be inside of W. So W is closed under vector addition and scalar multiplication. If we have a subset of V that satisfies these two properties, that means that W is also going to be a vector space, and in particular, we call it a subspace of V. Subspaces are very important vector spaces. They allow us to take vector spaces we already know and add some extra conditions onto them that might be necessary to solve a problem or to talk about solutions to a problem. We will see some particularly important subspaces that allow us to consider vector spaces of functions with the boundary conditions already built in. So, for example, let's first consider a subspace of C2, the space of twice continuously differentiable functions. Suppose we want to solve the steady-state heat flow problem with homogeneous Dirichlet boundary conditions. So we want a vector space that describes all the possible solutions for this problem. Well, to be a possible solution to this problem, you need to have the value of your function set to 0 on the boundary. Therefore, we define the subspace of C2 given by C2D. This is the set of all twice continuously differentiable functions such that the function is 0 on the boundary, such that it automatically satisfies homogeneous Dirichlet boundary conditions. So if a function is an element of this subspace, it will already satisfy the boundary conditions for a homogeneous Dirichlet problem. Similarly, we can do the same thing with homogeneous Neumann problems. We can define the subspace C2n that are all twice continuously differentiable functions such that the derivative at the boundary is equal to 0.